Welcome! In this session, we'll explore LeetCode problem number 278, first bad version. This problem challenges us to optimize the process of identifying the first defective product in a sequence. We'll discuss the problem, analyze potential approaches, and wrap up with insights and takeaways. Let's dive in. In this problem, you are acting as a product manager overseeing the development of a new product. Unfortunately, one of the versions of your product has failed the quality check. What makes this challenging is that any version developed after a bad version is also considered bad, since each new version builds on the previous one. Your task is to identify the first bad version in a sequence of product versions, numbered from 1 to n. To help with this, you are provided with an API called isBadVersion, version. This API takes a version number as input and returns a Boolean value indicating whether the given version is bad. The goal is to implement a function that finds the first bad version while minimizing the number of calls made to the API. The function you need to implement is called firstBadVersion, and it takes one parameter, n, the total number of versions. The API isBadVersion is already available to you. For instance, if there are 5 versions and version 4 is the first one that fails, the function should return 4. In this case, versions 1, 2, and 3 are good, while versions 4 and 5 are bad. The task is to identify the first version that caused the issue. Similarly, if there is only one version and it is bad, the function should return 1. This example demonstrates that even in the smallest input case, your solution should correctly handle the scenario where the first version itself is the problem. Now, consider a case where there are 10 versions, and version 7 is the first bad one. Here, versions 1 through 6 are good, and versions 7 through 10 are bad. The function should return 7, as this version marks the beginning of the failure. The explanation remains consistent: all versions before version 7 pass the quality check, and all versions from 7 onward fail. This example highlights how the function must find the exact point at which the versions transition from good to bad. To summarize, there are several constraints to keep in mind. The value of n, the total number of versions, can be as large as 2 times 10 to the power of 31, so your solution needs to be efficient. The API isBadVersion is costly to call, so minimizing the number of calls is crucial. The versions are numbered sequentially starting from 1, and you can assume there is always at least one bad version. Your solution should work within a time complexity of O log n, which suggests using a binary search approach. Additionally, edge cases must be handled, such as when the first version is bad, or when the last version is the first bad one. With these constraints and edge cases in mind, your implementation should be both efficient and robust, even for very large inputs. To solve the first bad version problem, we first consider the brute force approach. The idea here is straightforward: start at version 1 and check each version sequentially using the isBadVersion API. As soon as we find the first bad version, we return it. This approach has a key observation: since all versions after the first bad one are guaranteed to be bad, we only need to identify the first occurrence. While this method is simple and requires no extra space, its major drawback is inefficiency. The time complexity is O, n, meaning it scales linearly with the number of versions. For a large input size, such as 10 to the power of 9 versions, this would be computationally expensive and impractical. To address this limitation, we turn to a more optimized method, the binary search approach. Binary search leverages the fact that we can eliminate half of the search space with each step, significantly reducing the number of checks required to find the first bad version. The binary search approach takes advantage of the problem's monotonic property: once we encounter a bad version, all subsequent versions are also bad. This characteristic makes binary search an ideal fit, as it is designed for problems with ordered or monotonic behavior. The algorithm begins by initializing 2 pointers, left at 1 and right at n, the total number of versions. While left is less than right, we calculate the middle point mid using the formula left plus, right left, //2. At each step, we use the isBadVersion API to check whether mid is bad. If it is, we know the first bad version must be at mid or earlier, so we move our right pointer to mid. Otherwise, the first bad version must be after mid, so we move the left pointer to mid plus 1. When the loop ends, left will point to the first bad version, which we then return. This approach is highly efficient, with a time complexity of O log n, as the search space is halved at each step, and it uses O1 space since no additional memory is required. The result is a simple yet elegant solution that is much faster than the brute force method, especially for large inputs. Given the options, the binary search approach is the clear choice for this problem. Its logarithmic time complexity ensures it is highly efficient even for massive input sizes, such as 10 to the power of 9 versions. The problem's monotonic nature, where all good versions are followed by bad ones, makes binary search not only effective but also a reliable strategy for pinpointing the exact transition point. While the brute force approach is conceptually simpler, it is ultimately impractical for large inputs due to its linear time complexity. However, binary search does come with some trade-offs. It requires a solid understanding of the algorithm and careful implementation to avoid common pitfalls like integer overflow when calculating the midpoint. Nonetheless, the advantages of binary search far outweigh these challenges. It strikes the perfect balance between efficiency and simplicity, guaranteeing both correctness and scalability. For this problem, binary search is the optimal solution, leveraging the structure of the input data to deliver results quickly and reliably. To begin, the problem requires us to identify the first bad version in a sequence of software releases, numbered from 1 to n. We are given an API, isBadVersion, version, which tells us whether a specific version is bad or not. Importantly, if a version is bad, all versions after it are also bad. The challenge lies in finding the first bad version while minimizing the number of API calls. Let's start with the brute force approach. Here, we sequentially check each version, starting from 1. For every version, we call isBadVersion, version. As soon as we find the first version where the API returns true, we return that as the first bad version. If no bad versions exist, we handle this by returning a special value like -1. While straightforward, this method is inefficient, as it has a time complexity of O(n) in the worst case. Since we only use a few variables, the space complexity is O(1). Clearly, there's room for improvement, which is where binary search comes in. Now, let's optimize the search process using binary search. The idea is to leverage the sorted nature of the problem. Once a bad version is found, all subsequent versions are bad. First, we define our search space with low set to 1 and high set to n. Then, we enter a loop that continues as long as low is less than or equal to high. Inside the loop, we calculate the middle point, mid, as low plus, high low, //2. We then call isBadVersion, mid, to determine if the middle version is bad. If the result is true, this means the first bad version could either be mid itself or lie to its left. So, we narrow our search to the left half by setting high equals mid 1. On the other hand, if isBadVersion, mid, returns false, it means the first bad version must be in the right half, so we update low equals mid plus 1. This process continues until the search space is exhausted, at which point low will point to the first bad version, and we return it. The efficiency of binary search becomes clear when analyzing its complexity. The time complexity is O log n, because the search space is halved with every iteration. This is a significant improvement over the O(n) complexity of the brute force approach. The space complexity remains O(1), as we only use a few variables like low, high, and mid, with no additional data structures. This efficiency is possible because the problem's sorted nature allows us to minimize API calls, which is a key insight. Additionally, the algorithm handles edge cases gracefully. For example, it works correctly if there's only one version, n equals 1, if all versions are good, or if the first bad version is at either extreme of the list. These considerations ensure the algorithm is robust and reliable. Finally, the simplicity of the binary search approach is reflected in its implementation. We don't need any extra data structures, just a few variables to track the search bounds and calculate the midpoint. This keeps the memory usage at O(1), making the algorithm highly space efficient. The implementation begins with a brute force solution, which iterates over all versions and checks each one using isBadVersion. However, the optimized solution replaces this with binary search. By narrowing the search space based on the API's response, we achieve logarithmic time complexity. The code for binary search is concise: initialize low and high, iterate while adjusting bounds based on isBadVersion, mid, and finally return low as the first bad version. This approach combines efficiency, simplicity, and correctness, solving the problem effectively while minimizing API calls. This solution efficiently determines the first bad version using a binary search approach. The first bad version function takes the number of versions n as input. Initially, we define two pointers, left and right, representing the range of versions to search. The left pointer starts at 1, the first version, and the right pointer starts at n, the total number of versions. The key optimization lies in the binary search logic implemented in the while loop. The loop continues as long as left is less than right. Inside the loop, we calculate the midpoint mid using left plus, right left, //2 to prevent potential integer overflow. This midpoint divides the search range into two halves. We then use the isBadVersion mid API to check whether the version at mid is bad. If it is bad, it means the first bad version is at mid or earlier, so we adjust the right pointer to mid. Otherwise, we know the first bad version must be after mid, so we adjust the left pointer to mid plus 1. The loop narrows down the search range by having it in each iteration, making the algorithm highly efficient with a time complexity of O log n. Once the loop exits, the left pointer will have converged with right to the position of the first bad version, which we return as the result. This solution minimizes API calls and efficiently identifies the first occurrence of a bad version, making it ideal for large datasets where n can be very large, such as up to 10 to the power of 9. This is the Java implementation of LeetCode problem number 278, first bad version. The logic mirrors the Python implementation, utilizing a binary search approach to efficiently find the first bad version. Key differences include Java's type declarations, e.g., int, and the use of the extends keyword to inherit from the version control class. The method avoids integer overflow by using left plus, right left, /2 to calculate the midpoint. Here, we are working through an example where the first bad version is in the middle of the range. We are given n equals 5, meaning there are 5 versions in total, and the isBadVersion function returns false for versions 1 and 2, but true starting from version 3 onward. The goal is to find the first bad version using binary search. Initially, we set left to 1 and right to 5, which represents the entire range of versions. For the first iteration, we calculate the midpoint using the formula mid equals left plus, right left, //2. This gives us mid equals 3. Checking isBadVersion, 3, returns true, so version 3 is bad. Since we now know the first bad version must be at mid or earlier, we update our search range by setting right equals mid, narrowing it to 1, 3. In the second iteration, we calculate the new midpoint with the updated range. Using the same formula, mid equals 1 plus open parenthesis 3 minus 1 close parenthesis //2 equals 2. This time, we check isBadVersion, 2, which returns false, indicating version 2 is good. Since the first bad version must come after mid, we update our range by setting left equals mid plus 1, narrowing it further to 3, 3. At this point, left is equal to right, both pointing to version 3. This is our termination condition. We can now confidently return left equals 3 as the first bad version. The output of this example is 3. Now, let's consider a case where all versions are bad. Here, n equals 4, and the isBadVersion function returns true for every version from 1 to 4. We start with left equals 1 and right equals 4, covering the entire range of versions. In the first iteration, we calculate mid equals 1 plus open parenthesis 4 minus 1 close parenthesis //2 equals 2. Checking isBadVersion, 2, returns true, meaning version 2 is bad. Since the first bad version must be at mid or earlier, we update the range by setting right equals mid, narrowing it to 1, 2. In the second iteration, we calculate a new midpoint. With the updated range, mid equals 1 plus open parenthesis 2 minus 1 close parenthesis //2 equals 1. Checking isBadVersion, 1, returns true, indicating version 1 is bad. Since the first bad version must still be at mid or earlier, we set right equals mid, reducing the range to 1, 1. At this point, left equals right, both pointing to version 1. This is our termination condition. We can return left equals 1, indicating that version 1 is the first bad version. The output for this example is 1. This time, we examine a scenario where there are no bad versions at all. Here, n equals 3, and the isBadVersion function returns false for every version from 1 to 3. We initialize left equals 1 and right equals 3, covering the entire range. For the first iteration, we calculate mid equals 1 plus open parenthesis 3 minus 1 close parenthesis / 2 equals 2. Checking isBadVersion, 2, returns false, so version 2 is good. Since there are no bad versions at or before mid, we update the range by setting left equals mid plus 1, narrowing it to 3, 3. At this point, left equals right, both pointing to version 3. However, since isBadVersion, 3, is also false, it confirms that no bad versions exist within the given range. The algorithm handles this situation by returning none or another problem-specific value to signify that there is no bad version. The key takeaway here is that the binary search algorithm repeatedly cuts the search space in half based on whether isBadVersion, mid, is true or false. If the result is true, we move the right pointer to mid, and if it's false, we move the left pointer to mid plus 1. The process terminates when left equals right, pinpointing the first bad version or confirming its absence. The time complexity of our solution is O log n, thanks to the use of binary search. Here's how it works. The algorithm begins with a search range spanning from 1 to n. On each iteration, we calculate the midpoint of the range and check if it's a bad version using the isBadVersion function. Based on the result, we either narrow the range to the left or the right half by updating the values of left or right. This halving process continues until the left and right pointers meet, which determines the first bad version. The number of iterations required to converge is proportional to log base 2 of n, as the range is halved with each step. Since each iteration involves a single call to isBadVersion, which runs in constant time O(1), the overall time complexity is O log n. Even in the best case, where the first bad version is found immediately, the algorithm still adheres to the binary search process, maintaining a logarithmic time complexity. For the average and worst cases, the process consistently requires log_2, n, iterations, confirming that the time complexity remains O log n in all scenarios. The space complexity of this solution is O(1), meaning it uses constant memory regardless of the input size n. This is because the algorithm does not rely on any additional data structures that scale with n. Instead, it only uses a few integer variables, left, right, and mid, all of which occupy a fixed amount of memory. Additionally, the function avoids recursion, which means there's no extra memory consumed on the call stack. Since the memory usage does not change as n grows, the space complexity remains constant, making the solution very efficient in terms of space. To better appreciate the efficiency of the optimized approach, let's compare it to a naive solution. The naive approach would involve iterating through every version from 1 to n and checking each one with isBadVersion. This results in a time complexity of O(n), as up to n calls to isBadVersion are made. However, even in this approach, the space complexity is O(1), because no additional memory is used beyond a few variables. In contrast, the optimized binary search approach drastically reduces the number of isBadVersion calls to O log n, making it significantly faster for larger values of n. Importantly, the space complexity for the binary search approach also remains O(1), so while both approaches are space efficient, binary search is clearly the better choice in terms of time efficiency. To mathematically prove the time complexity of O log n, let's analyze how the binary search reduces the search range. At the start, the range size is k, where k equals n. After the first iteration, the range is halved, becoming n divided by 2. After the second iteration, it's halved again, becoming n divided by 4. After m iterations, the range size is n divided by 2 to the power of m. The binary search stops when the range size is reduced to 1, which gives us the equation n divided by 2 to the power of m equals 1. Solving for m, we find that m equals log base 2 of n. Since each iteration performs a constant time operation, specifically a single call to isBadVersion, the total time complexity is proportional to the number of iterations, which is O log n. This mathematical proof solidifies our understanding of why the algorithm is so efficient. When working on the first bad version problem, there are a few common mistakes to watch out for. First, not recognizing this as a binary search problem is a frequent issue. The isBadVersion API provides a monotonic behavior, meaning once you find a bad version, all subsequent versions are bad. If you treat this as a linear search problem instead, you'll end up with a time complexity of O(n), which is highly inefficient for large inputs like n equals 100,000. Instead, binary search reduces this to O log n, making it much faster. Another mistake is calculating the midpoint incorrectly. While the formula, low plus high, /2 might seem straightforward, it can lead to integer overflow in languages like Java or C++ when low and high are very large. Using low plus, high low, /2 avoids this issue. Additionally, you need to handle edge cases carefully. Examples include when the first version is bad, when there are no bad versions at all, or when the input size is very small, like n equals 1 or n equals 2. Overlooking these details can lead to incorrect results or runtime errors. Lastly, avoid calling isBadVersion unnecessarily within the same iteration. Each API call has a computational cost, so minimizing the number of calls is key to maintaining efficiency. Another common pitfall in binary search is off-by-one errors. These happen when updating low or high incorrectly, such as setting low equals mid instead of low equals mid plus 1. Errors like these can cause infinite loops or incorrect outputs, so it's important to double-check your boundary adjustments. Now, from an interview perspective, you must recognize that this problem is a classic example of a monotonic function. The isBadVersion API divides the versions into two segments, good versions and bad versions, making binary search the optimal approach. It's critical to explain your thought process during an interview. Clearly articulate how binary search reduces time complexity from O(n) to O log n, and why that's significant. If the problem involves an external API, emphasize efficiency by minimizing calls to it. This shows that you're mindful of performance. Additionally, testing edge cases is vital before finalizing your solution. Examples include scenarios like n equals 1, n equals 2, the first version being bad, the last version being bad, or no bad versions at all. Finally, be prepared for variations of this problem, such as finding the first occurrence of an element in a sorted array or finding the minimum in a rotated sorted array. These are conceptually similar and often appear in technical interviews. The first bad version problem is closely related to a few other problems you might encounter. For instance, LeetCode 704, which is the basic binary search problem, and LeetCode 852, which asks you to find the peak index in a mountain array. Another related problem is LeetCode 162, where you're tasked with finding a peak element. These problems share the core principle of binary search and can help reinforce your understanding of how to apply it effectively. Now, while binary search is the optimal approach for this problem, it's worth discussing alternative methods. A brute force linear search, for example, is straightforward to implement but has a time complexity of O(n). This makes it impractical for large inputs, so it's only suitable when constraints are small. On the other hand, optimized binary search, with a time complexity of O log n, is far more efficient but requires careful handling of edge cases. You also need to be cautious about common pitfalls like integer overflow or off-by-one errors. Understanding the trade-offs of each approach will help you make the right choice based on the problem constraints. Another variation to consider is recursive binary search. This approach maintains the same time complexity of O log n, but it introduces additional space complexity due to the recursion stack. While it's not as memory efficient as an iterative solution, recursive binary search can be helpful for conceptual clarity. It provides a cleaner and more intuitive way to express the logic of binary search, which might be useful in scenarios where readability and simplicity are prioritized. However, in practice, the iterative approach is generally preferred for its efficiency and lack of additional memory overhead. Being familiar with both methods allows you to adapt to different requirements and constraints in coding challenges or real-world scenarios. Thank you for joining me in solving first bad version. We used binary search to optimize our solution, achieving O log n time complexity. Remember, binary search is a vital skill for tackling sorted data problems. If this was helpful, don't forget to like, share, and subscribe for more content. Keep practicing and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!